Okay. So what's happening on some of the problems, and a lot of us are making the same mistake. Let me pull up the key for a moment. We have by the way, most people did a really good job on the first one. That's probably the hardest problem we've looked at. The L'Hopital on the exponential, that was really good. So the second problem, we're at this point of the problem. Okay, and what's happening is the majority of folks are saying, let me do a formal U-substitution. Great. Off to the side, I'd say, let U equal 1 plus x cubed, then du is 3x squared dx. And here's the problem. We're now writing the following. And this will be u to the negative 1/2 du. Okay, I'm going to stop right there. It doesn't matter what I write next. Not only is this absolutely incorrect in every conceivable way, this is d and e. You have 1 over root 0. Remember, that's the other evil kind of indeterminate form, but because it's a one-sided limit, there is no limit. This is a d and e. Anything I write after is just BS. It's garbage, because this was absolutely incorrect. Now, I have to remind people, when you're doing a definite integral and you change the limit, the variable, you absolutely have to change the limits. There is no exception. Now, you can do the antiderivative off to the side. That's legal, and then come back. But in a definite integral, when you change the variable, you have to change the limits. And in a definite integral, under no condition do you ever change back. There is no such mathematics, because this is a numerical value. All I have to do is have the right limit here, then I proceed from there. We've gone over this before. I've got post-it notes and all this. Some of us have just gotten a little bit lazy and a little bit sloppy. So just do the general antiderivative off to the side, find out what the antiderivative is, and then come back. But what you can't do is leave the old limit, because this is a d and e. This doesn't equal anything, and this doesn't equal infinity. This doesn't equal anything, because that's not a one-sided limit. You were taking the limit of this guy. That can't be a 0, because this is undefined there. So we gotta stop doing that one. The second one of these was much, much simpler, so nobody really did a substitution at all. But that one right there, we've got to get this one out of our system. Now, the other thing I'm seeing, and this is just silliness. Okay, we've got to this point here in the problem. We've got 2/3 limit as c goes to infinity of the square root of 1 plus c cubed minus 1. And here's what I'm saying. And this is equal to 2/3 times the square root of 1 plus infinity cubed. Infinity is not a scalar. Infinity cannot be inserted into an equation. You can't take a function of infinity. Infinity in any algebraic manipulation is always completely incorrect, because if I can treat this as a constant, then this is 1. This is 0, because you're treating it as a constant. No, infinity is the result of a limit, not a result of a calculation. I can't insert an infinity. I'm getting on the last one was great. I had people writing, and it's e to the negative 2 infinity. I'm getting that kind of stuff. That's just really terrible mathematics, because you're saying that's a constant. The moment you insert infinity into the statement, the answer can't be infinity, because if you're saying this equals infinity, algebraically, that's an impossible mathematical statement. E to the negative 2x can't equal x ever for any value. So that's impossible, because you put the infinity in the wrong place. So let's get that out of our system right now, because your solutions should make sense. And when we use infinity as a constant, they don't make sense, because then when we get to the indeterminate forms involving infinity, we're not going to be sure what to do with them. So when you say, oh, this is going to be infinite, then just say the answer is infinite. And again, most of you are doing most of it correctly, but we're throwing a statement or two in there. Sometimes it just doesn't make any sense.
Professor,
yes.
So for that last one, is it, so.
Which line you talking about, problem 2 or problem
number 3? Number 3. So as far as like the very last step, when you're evaluating, is what you're saying actually like physically inserting infinity wrong, but
Don't insert infinity.
conceptually,
You should have a statement that looks something like that.
sure.
So you're saying, now here's the tricky thing. Depends what C is doing. Is C going to 0? Is C going to 5? Is C going to infinity? Do you agree? It kind of depends on what C is doing.
Yeah.
Okay, as C grows without bound, this exponent's growing without bound, which means my denominator's growing without bound, which means it's getting infinitesimally small.
So that's equal to 0.
Here's the kind of thing I would do. This is my mental scratch. This term is going to 0. Or if you want to say it this way, you could say that term is going to infinity. That would be a correct interpretation.
Okay.
That term is approaching infinity. Terms cannot equal infinity. Terms can approach infinity. Limits can equal infinity. So either by saying that quantity approaches infinity or that quotient approaches 0, to convince yourself, okay, I'm going the right way. Because here's the other thing. This is a small thing, but it can also be a huge thing. I did all of this correctly. And then I said my answer was infinity. I mean, think about it. You did everything correctly. This term approaches 0, so my answer is just -1/2 times -1. But because there's something infinite in the middle of the problem, it's easy to see how I could accidentally interpret this as being infinite rather than 0. So we did everything right, and we said the answer is infinity. The funny thing is, I consider that lesser of an error because you saw something went to infinity. You just weren't mentally thinking the denominator was going to infinity. You know, that one, you just got to be a little bit sharper. That's just better.
Right. But as far as like actually like inserting infinity into it to evaluate, that is wrong. Okay.
Yeah, because C is approaching infinity. You don't ever get to infinity.
Right.
Yeah. It's like my kids would say, you know, I want infinity cookies. So I'll be counting my infinity -3, infinity -2, infinity -1, infinity. Okay, we're there. You know, I did that when they were kids. Since I can't physically get to infinity, infinity is not a constant. And we sometimes forget that infinity is a destination. It's that way forever. If you could actually physically get there, that would mean it's finite. And that kind of contradicts all the other things. So dealing with infinities in calculus has always been one of the biggest issues people face. So we want to get around it and not make it harder than it needs to be. It's hard enough. Now, today we're going to talk about series. We're just going to get our feet wet. Now, what is a series? Well, I mentioned last day, a series is a sum of the terms of a sequence. So if I have a sequence.
Wait, Professor, have you actually posted the key to the quiz yet? Because I don't see it.
Did I not post it? Hang on a second. You might be right. I thought I did. Let me bring up Canvas. Is it there? What is this one? This quiz, this is 10?
Yeah, quiz 10.
Oh, you know what? I had, but then I got distracted and I pulled it back. Okay, now it's posted. Let me bring it up. Thank you for the reminder. I got a couple of reminders that people were looking on Canvas and said, oh, Mr. Brown, you still haven't posted the lecture from March 8th. I had to look at my schedule. That was the test. So if I post the video from March 8th, it's going to be really boring. It's going to be all of you staring at a piece of paper for, you know, a couple hours. So I'm not going to post that one. Yeah, I mean, it might be exciting to look at the top of people's heads or, you know, whatever. So if I have the sequence defined by AN, that means, you know, A1, A2, forever and ever and ever and ever. Then we say that capital S stands for sum, is equal to the summation from n equal 1 to infinity of AN. Now, hopefully everybody has used the symbol because we use the symbol a lot in Calc 1 when we're doing things. So a reminder, the capital sigma, that's what that is, the Greek letter sigma. The capital sigma always refers to sum. In every context you'll see it, it means sum. N is the index or the counter. Counter starts at whatever I'm telling you it starts at. I could start it at 75 if I wanted. I could start it at 0, but it starts at 1 and counters increment by 1. So this means A1 plus A2 plus A3 forever and ever and ever. Okay, that's all that means. The infinity means I'm never going to stop. Now, a lot of folks will say, and a lot of calculus textbooks will say, we're going to talk about the infinite series. The word series means infinite sum. So to say the infinite series, to me, it's the equivalent of, in geometry, when you're talking about the straight line, as opposed to those other kind of lines. Or my favorite one is, I actually have talked about the round circle. That's kind of redundant. A series means it's infinite, period. You don't have to say infinite series. Series means there's one of these. But what if? What if I only want the first 5 terms, or the first 10 terms, or the first 1,000 terms? What if I want a finite amount of terms? Then we write it like this. And I'll use a different index this time. This says I want A1, A2, but I'm stopping at AN. I'm adding up the first n terms. This one is generally referred to as S with a subscript of n. And this is called the nth partial sum. Yeah, and there are times when this is beneficial. In your algebra classes, and even in my discrete math class, it's often the case. When we're doing Riemann sums in calculus, remember, you had a finite sum and then you took a limit as the number of terms approached infinity. So what we do in calculus is we often do this, and then we take a limit. So I'm going to define that one in a moment. So there's exactly 2 ways that I can deal with the series. I can deal with all of it or some of it. Okay, that's all that means. Now, with that said, algebraically, that means that this, let's say you wanted to just for fun, I want the first 100 terms. Okay, but I want to put an equal sign between these. So then what would I do? This says add up the terms from 1 to 100. This says start at 101. Keep going. So that's always true. As long as I pick up, okay, the next term, you can always do this. So this term right here would be Sn. I'm sorry, this term right here would be 100, and this would be S minus S100. There are reasons that you might want to do this, practical reasons that might help us in the long run. So this is a little bit of the algebra of limits. So I want to go over a couple other very, very simple rules. I should say of series. A couple of very simple rules for series. These are things that you probably saw in a baby algebra class. I mean, they're not really complicated concepts. So we'll start with the partial sums just to make it simpler. So if I said, consider the partial sum from, let's say, I equals 1 to n of AI plus the sum I equal 1 to n of BI. It's easier if I do these as finite things. Well, the first one is A1 plus A2 all the way up to AN. The second one is B1 plus B2 all the way up to BN. I love the ... It saves me some time. Assume n is large and that you don't want to write all the in-between terms. Now, using just some really simple algebra, I know that addition is commutative. I know that addition is associative. Commutative means I can rearrange. Associative means I can regroup. So we know then this quantity is the same . Oops, AN. So stare at that for a moment, convince yourself. I just rearranged, this plus this plus this and so on. But what is this? This is the sum of AI plus BI. Oh. The sum of the summations is the summation of the sum. That sounds kind of like isn't the sum of the limits the limit of a sum, and the sum of the derivatives is the derivative of a sum, and the sum of the integrals is the integral of the sum? Yeah, it's the same property. It also holds for series. So the sum of the series is the series of the sum, as long as, by the way, I begin and end at the same place. So if I made both of these infinite, then this would still be a true statement for the infinite. That's a very, very important property. What it means is if I'm starting with this, I can break it up at my convenience, or if I'm starting with this, I can add them together at my convenience. Whatever works. And then the only other rule we will apply is what if I had something like this? I want the sum of KAI from I equal 1 to n. Well, this would mean I have KA1 plus KA2. Remember, the numbers are subscripts, they're not multipliers. Okay. Okay, that's pretty exciting. But I can factor out the K. And then that quantity on the right was nothing more than the sum. What does it appear I just did? It appears I factored out the scalar. So the summation of a constant times a sum, or I should say, I'm sorry, the summation of a constant times a term. Did you say Kai? That's your name. Clever. Okay, this got me all distracted there. The summation of a constant times the term is the constant times the summation. And again, that's like a limit, derivative, and integral property of pulling constants. Those are the only ones. Things like the summation of a product is not the product of the summations. Right? The summation of a function is not the summation function of the summations. Only the sums and scalar multiples hold. Okay. So with those, there's a couple more small little things we can say then. Because we're going to look at 3 very, very important types of series today, very specific ones, and talk about their conclusions. So if I had something like this, I have the sum from I equal 1 to n of AI. We know what that is. We're calling that Sn. And we're calling this one S. How can I get from here to here? Anybody? One word. How can I get from the partial sum to the infinite sum?
Limit?
A limit. Very specifically, limit of what? What limit would I be taking?
Limit of n as it approaches infinity?
Beautiful. If I take a limit as n approaches infinity, I might be able to pull this off. So here's what we actually said. This is an extremely important thing. If I said this, that is always true. So one of the ways we sometimes calculate this infinite sum is that we figure out a way to write the partial sum, come up with some closed form to write the partial sum, and then we take the limit of that thing. We're going to do one of those today. This is very practical because a lot of times I'm going to give you the summation and say, what does it add up to? You're going, I have an infinite number of terms. I can't add all these up. But if I could add up a finite number of terms and see a general pattern, that's the key. If I can see a pattern, then I might be able to take a limit of that thing. And that's really, really handy. We're going to do that a couple of times today. So this is always true. Now, what if the limit doesn't exist? What if it's one of those DNEs? Well, then it means the infinite sum doesn't exist. That's okay. What if it's infinite? Well, then it means my infinite sum's infinite. That's okay. Now, we talked about sequences last day. There were 3 possibilities. My sequence could converge to a number, my sequence could diverge to infinity, and my sequence could diverge without limit. Turns out sums are the same 3 things. A sum can converge to a number, a sum can diverge to infinity, and a sum can diverge without limit. Okay, and a lot of it has to do with the behavior of the sequence too, by the way. All righty. So with that, the first and foremost one, and by the way, I've got lots of posted lecture notes that are just like 1-page short bites. And I think I posted 3 different ones for today's lecture alone. It would be really good for you to take a peek at those even afterwards, especially if you're not a great note taker to begin with, because I've got it really concise and summarized. Let's go back to the geometric. Okay. Remember the geometric sequence? That was the one where we said the nth term, we figured this out last day, was the first term times r to the n minus 1. Remember, we did this last day. So a geometric sequence is one where I'm multiplying the same term. You know, so it might be 2, 6, 18, 54, you know, forever and ever and ever. So a geometric series is obviously I'm going to add these terms. So if I were to add the terms, well, shoot, obviously these are going to grow without bound. That's going to get infinitely large. But what if my R is a fraction and I'm making my terms smaller? Ooh, that's different. That one might actually be worthwhile. So here's what we want to look at. I just want to start with the following. R to the n, and now I want to take the limit as n goes to infinity of R to the n. Now, here's where having a calculator might be really useful, because this is extremely difficult to conceptualize because there's cases. And mathematically, we don't love proving things when there are cases, but there are several cases here. All right. Obviously, if R equaled 0, that'd be boring, but the answer would be 0. I don't care about that one. So I have several cases. I have R is greater than 1. I have R is equal to 1. I have R is between -1 and 1. I have R is equal to -1, and I have R is smaller than -1. So think of this as large positive number, large negative number, exactly 1, and then all the numbers in between. The last one is equivalent to saying the absolute value of R is less than 1, by the way. That's what that is equivalent of. Now, it's not very hard, because if I said, what does the graph of this look like? If I don't think of it in terms of 1, 2, 3, 4, 5, think of it like, y equals 2 to the n, e to the n. What? I have an exponential function. So if the R is greater than 1, I know this grows without bound. No question, that's going to be infinite. Piece of cake. Okay. What if R is exactly 1? Then wouldn't 1 to the nth power just be 1? Now let's go to the other side. This is the most, well, both of these are pretty evil. When R is -1, now what is n? N is the index. N is 1, 2, 3, 4, 5, 6, 7, 8. N is not any real number, because if n were any real number, then this would be imaginary. So no, we're not doing that. N is the integer exponent, 1, 2, 3, 4, 5, and so on. But if I put a 1 in there, then I'd get -1 to the first, -1 to the third, -1 to the fifth, -1 to the odd exponent's -1. But if I put -1 to an even exponent, yikes, then -1, right? Then it would be positive. So I can't really do that, guys. So this is going to be a DNE. Now this one's even worse. This is actually the worst kind of all. So if R were a large negative number, then I'm going to be bouncing back and forth between positive, negative, but I'm growing. So it'd be kind of like this. This is the most evil of all of them. These are both DNEs. If I have a negative number and I'm raising it to powers successively, so I'm going to get DNEs. Another way of saying it is this limit diverges without limit for both of these cases. It's infinite here, so now here's the big picture, right? That guy right there. Now, if I take a value of R that is between -1 and 1, it's smaller than 1, but I'm taking the limit as the exponent goes to infinity. Well, obviously, if R is 0, my answer would be 0. That's not really the question. So here's one way to do this. Get out your calculator, and let's take a number that's really close to 1, like 0.999. I'm going to take 0.999. Okay. Now I'm going to raise 0.99 to I'll raise it to the millionth power. 1, 2, 3, 4, 5, 6. Okay. And now hit equals. Hey, wait a minute. My calculator just said it equals 0. No, it doesn't equal 0. You can't take a non-zero value, raise it to a power, and get back 0. So why the heck did my calculator just say it equaled 0? Because it's so small that it had at least 99 zeros after the decimal point, because your calculator probably can only go up to 10 to the -99th power. So in other words, my calculator is telling me this is a decimal value with more than 99 zeros after the decimal place. It's that small. Oh, so if I take a number really, really, really close to 1, I don't have to go very far with the exponent before it's microscopic. That tells me a lot, doesn't it? That says if R is between 0 and 1, certainly, this is going to approach 0. Now, what if r is on the negative side? Well, let's do the exact same thing. Let me take negative 0.999 and let me raise that to a power. Again, I get microscopically small. Actually, no. When I raised it to the 100,000th power, I got approximately negative 3.5 to the negative 44th power, or times 10 to the negative 44th. But when I raise it to the millionth, I get 0 again. That means essentially everything in this range is getting smaller and smaller and smaller. Whether it's positive or negative, it's getting smaller and smaller and smaller and closer to 0. So this limit is 0. And that's the most important of all of them. If I said, what is the behavior of this? It diverges to infinity when I'm bigger than 1, diverges without limit if I'm more negative 1 or worse, and it's equal to 1 exactly in that situation. But I don't know if I like that guy. I like that guy the best because he's easiest to deal with. So now let's go back up to here. Okay, now that we have this information here. All right. So I have a geometric sequence, looks like this. I want to add up the first n terms. That means I want you to do the following. Okay, but let's replace these with the actual terms from the geometric sequence. So that means this is a1 plus a1r plus a1r squared. I'll go out a little ways. Plus a1r to the n minus 2, and then finally plus a1r to the n minus 1, because we know that's the nth term. Okay, first term, second term, third term, second to last, last term. I would like to add these up. I can factor out an A1, that's fine, but I have different exponents for each term. So that's really not, this is not going to be easy to do. And if n is large, is there something else maybe that's I can do that's clever? Did somebody figure out something truly clever? Yes, somebody figured out something truly clever. What is negative r times Sn? This is Sn. What is negative r times this? Well, multiply every term by negative r. So that'd be negative a1r, negative a1r squared, negative a1r cubed, negative a1r to the n minus 1, negative a1r to the n. I just took every one of these terms and multiplied it by r, so all the exponents got shifted up 1 and negative. So all negative, all the exponents are 1 greater. And here's what I'd like to do. I'd like to add these quantities. So the quantity on the left is simply Sn minus n times Sn. That's the left. But the right side, this is the part I love. When I add these, those will cancel. Those will cancel. This will go all the way down the line. Those will cancel, right? All the way down the line, everything's going to cancel except that one and that one. So you notice that? So whoever figured this out, I mean, pure genius. If I take this sum, this finite sum, and I multiply every term by negative r, and then I add them, these are the only 2 terms that are left over. Beautiful. So now over here, let's factor out the Sn. Over here, let's factor out the A1. So finally, I'm going to put up here, for this particular sequence, the sum of the first n terms is A1 times 1 minus r to the n. Oh, I'm sorry, this is it. I wrote an n, sorry. Let me fix that. That's an r. I can't read my own writing. Over 1 minus r. Now, a lot of you might remember that formula from baby algebra. That's how you add the terms. Now, the nice thing is, if n is a finite number, then that's a finite number regardless of the size of the r. But what I'd like to know is, I want to take a limit. I want to be able to calculate the infinite sum. So let me erase this. So now I have an infinite sum. I have a geometric series. So this is still my nth term, but now here's what I want you to add up. I want to add up from n equal 1 to infinity of a1 r to the n minus 1. So again, if I start from scratch, that'd be a1 plus a1r plus a1r squared forever and ever and ever. Okay. But how do I add up an infinite number of terms? Well, technically, shouldn't this equal the limit as n goes to infinity of Sn? That's what we just said a moment ago. Oh, so I need this. Okay, so that should be the limit as n goes to infinity of a1 1 minus r to the n over 1 minus r. Now, the problem is if r is big, we know this is going to be infinitely large because I'm adding up numbers are getting bigger and bigger and bigger. And if r is big negative number, we know it's going to go crazy wild. So I'd really like to know, when is this going to converge? When can I actually get a finite value? I don't care when it diverges. I only want to know when it converges. I want to know, when can I say this is the answer? It's this specific value. Well, it kind of depends on that guy right there, because that's the only thing that has an n in it. And we know about limits. The limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits. I can move the limit all the way inside. So technically, the following statement is technically equal to this. Because the only term that the limit's affecting is that one. I'm going to move it all the way on the inside. Okay, so we just saw a moment ago, right, when this thing is going to fail and when it's not going to fail. Now, let's go look at the infinite sum for a moment. A moment ago, we looked at the individual limits, and when r was bigger than 1, it clearly got infinitely large. That's kind of obvious. I'm adding bigger numbers forever. When r was less than or equal to -1, we saw it diverged without limit. And when r equaled 1, well, let's look at it. If r equals 1, then I'm adding a1 up infinitely many times. See, if r equals 1, then it's a1 plus a1 plus a1 plus a1 forever and ever and ever. So clearly that's going to get infinitely large, isn't it? So it really comes down to, if r is between -1 and 1. If r is between -1 and 1, then this term here will approach 0 if, like I said before, that's true. If that is true, that term will approach 0. So if that is true and that term approaches 0, what does this leave? a1 times 1 minus 0, or simply a1 over 1 minus r. And that, folks, is a truly cool and extremely powerful formula. A geometric series will actually converge to this value if the absolute value of r is less than 1. In all of the cases, it diverges. That's it. It diverges in every other situation, but if r is smaller than 1 in absolute value, it will converge. Let's do a couple of examples of that, just to kind of convince yourself. One of the most classic problems that we've looked at, and you've probably seen this one before. I like to say it like this. I'm going to start at one wall and I'm going to walk halfway across the room. And then I'm going to walk half of that. And then I'm going to walk half of that. And I'm going to continue walking half of that. So I'm going to take a half plus a fourth plus a eighth forever and ever and ever. Technically, it's going to look like this. When n is 1, I'm a half. When n is 2, I'm a fourth. When n is 3, I'm an eighth. And I'm going to do this forever and ever and ever. I would like to know what this adds up to. Let's suppose I actually have all the time in the world. I have forever. So another way of thinking about it, as I'm moving across the room, the distance between me and the other wall is getting smaller and smaller and smaller and smaller. That distance is approaching 0. It never equals 0, but it's approaching 0. So it makes sense. If I had forever, it's kind of like, do I get to the other side? Well, if I add this up, what's my A1? Half. What's my R? Looks like I'm multiplying every term by a half. So according to this rule here, this is the infinite sum. My infinite sum should be the first term over 1 minus R, which is a half over a half, which is in fact 1. Oh, that's so cool. So this is something, by the way, I would have hoped you did in your remedial algebra class. You did problems like this. Geometric series do converge when R is small, and they're very, very useful from that standpoint. So I can always do this. All I have to do is recognize what the A and R are. Now, there's a couple of really nice features of this. So let me ask you the following. Let me change the way I ask the question. All right. Let's find the sum. How about, excuse me, 81 plus 54 plus 36 plus 24 plus ... This is going to go forever and ever and ever. And I want to find this sum. So all I got to do is produce the rest of the terms forever. That might take me a few minutes. And then I want to add up those terms forever. That might take me a few more minutes. Maybe that's not practical. Or recognize 54 over 81, 36 over 54, 24 over 36, those all equal the same value. Though it's all equal 2/3. So this is a geometric series with first term 81 and constant ratio 2/3. And I know that because 54 over 81, 36 over 54, 24 over 36, they're all 2/3. I can now tell you the infinite sum. Now, if I just simply added these numbers, that's not the infinite sum because I'm going to continue adding numbers forever. You know, the next number is going to be plus 16, right? It's going to keep going. I'm not even going to dip below 1 for a little while. But the infinite sum is first term over 1 minus the constant ratio. That would be 81 over 1/3 or 243. This will add to 243, which is just beautiful. And that was not very much work. So calculating a geometric series is easy if R is small. It's a simple formula. Does it ever fail? Ooh. All right, let's try another one. Find the sum. And let's say it's 2 plus 6 plus 18 plus 54 plus 162 plus. All right. So my first term is a 2. My constant ratio clearly is a 3. So my infinite sum is obviously 2 over 1 minus 3, which is 2 over negative 2, which is Houston, we have a problem. 2 plus 6 plus 18. These are getting bigger and bigger and bigger, and they're all positive. My sum is -1. What do you think? Did something
The
go?
formula doesn't apply when R is greater than 1.
Oh, yeah, you're right. I just said it only works when the absolute value of R is less than 1. My R is bigger than 1. I don't have to do anything. This diverges to infinity. The formula doesn't apply because my R wasn't smaller than 1. And I'm showing you the error, not an error. This is the only error anybody makes, is they apply the formula that only works when R is smaller than 1. And we're going to be using this for the next month. It's going to keep showing its ugly head. Well, no, it's happy, pretty face often. So that didn't work. All right, let's try another one of similar nature. So let's do another what if. So I've got, I think I'll keep it simple. I've got 1 minus 2 plus 4 minus 8 plus 16 forever and ever and ever. Well, let's see. If I take the ratio of consecutive terms, clearly my R is -2. But once again, if I add up the first two terms, it adds up to -1. If I then add the next term, I'm now up to +3. If I add the next term, now I'm at -5. If I add the next term, now I'm up to +11. My partial sums not only are getting larger in size, but they're alternating sign, aren't they? Ooh. So as I'm moving out, I'm going to do this oscillation that's getting bigger and bigger and bigger. If I tried that formula, obviously it's incorrect. I'm pretty sure this doesn't add up to a third. No, this is the worst. Anybody know what the answer to this is?
Does not exist.
Without limit.
That's not, my choices are converge or diverge.
Diverges without limit.
Diverges without limit. By the way, the limit does not exist. That would be true. If I said, what's the limit? -2 raised to the nth power, what's the limit? That limit doesn't exist. Therefore, we'd say this one diverges without limit. Because no matter where you stop, you're going to be a bigger number and opposite signs. This is the most evil of all of them. But the moment I had this, I could stop. Okay? The moment I had this, I could stop. And here's big picture. This one is growing without bound exponentially. I can follow its, I can wave at it. This guy here is bouncing back and forth between heaven and hell and just hasn't made up its mind yet. This one's horrible, but they both diverge. So in the long run, I like it when you can actually make this distinction. For now, this is really good because it means you really understand what the heck's going on. But more importantly, they both diverge, meaning neither one of them has a finite limit. Neither one of them can give me a number that I need. So diverging versus converging is kind of our main goal. If you can pinpoint the nature of the divergence, that's better. But just the divergent part is by far more important. Okay, so that's a geometric series. Those are very cool and very, very easy to work with overall. Let me show you one of the really cool applications that I'm guessing many of you actually did. Now, we know that the definition of a rational number, that's any number that can be written as a quotient of integers. So the number 5 is rational because I could write it as 5 over 1 or 10 over 2 or 15 over 3. So in other words, it has an infinite number of equivalent representations that are all quotients of integers. All rational numbers either have a terminating decimal sequence or an infinite repeating pattern. So we know 1/2 is 0.5. We know 1/3 is 0.3. We know stuff like that. What if I have a longer sequence? What if it's like, I don't know, 3/14ths, 2, 1, 4, 2, 8, 5, 7. Yeah, there. Don't ask, I can't explain. Those 6 numbers are going to repeat forever. Every fraction either has a terminating decimal or has an infinite repeating pattern. What makes a number irrational is it has an infinite decimal sequence that never repeats a pattern. That's the difference between rational and irrational, is the decimal sequence. So what if I gave you the decimal sequence? Everybody here with a calculator in hand can easily convert a fraction to a decimal. That's not exactly challenging. But can you convert the decimal back to the fraction? Okay. Let's start with an easy one like 1/3. 1/3 is this, which we sometimes will write it as 0.3333. Same thing. So how about if I wrote it this way? 0.3 plus 0.03 plus 0.003 plus. Could I do this forever and ever and ever? Yeah, I'm just moving the 3 to the next decimal place. Well, why would I do such a crazy thing? Because I've just made it into a geometric series. This is a geometric series. My A1 is clearly 0.3. What's my R? Anybody?
1/10.
1/10 or point. In this case, I'd say 0.1 just because it's a decimal already, but 1/10 is absolutely correct. So my infinite sum should be first term over 1 minus, well, what's that? That's 0.3 over 0.9, which is 1/3. Oh, that is so cool. Well, yeah, but that one was easy. Let's do one more complicated. By the way, can you always do this with a fraction, with a decimal? Yes. There is no exception. What I just did, you can always do as long as you have the repeating pattern. It is possible to always work backwards. So let's take something just slightly more complicated. All right. What if I've got something like 0.45? I'm repeating that decimal sequence. Well, let's write it down. That would be 0.45 plus 0.0045 plus 1, 2, 3, 4. So you notice what I did? Now it's going to be 2 zeros at a time because I have 2 numbers that have to keep moving. So here my A1 is 0.45, and what's my R?
0.01.
0.01? 0.01. Okay. Or 1/100th, if you will. The moment I write that down, my answer is seconds away if I'm doing this right. So my infinite sum is 0.45 over 1 minus 0.01. That's 0.45 over 0.99. Could I write that as 45 over 99? Is that legal? I just multiplied top and bottom by 100, but you know, I have a common factor there. I think that's 5 over 11. Huh. You don't suppose 5 divided by 11 equals, oh my gosh. Yeah. It's cool. You can always do that. This is just nice. This isn't big picture, but this actually allows us to do certain things that are very, very, very powerful statements mathematically. So I'm going to give you a very powerful statement. I'm going to blow your mind. You can make some money at a party this way, you know. Okay, how do you interpret 0.9 with a bar over it? What is that telling you? So 0, then what?
Infinitely repeating nines, it's a 1.
Yeah, infinitely repeating nines. This is equal to 1. This isn't rounded to 1. This isn't approximately 1. This is identically equal to 1. 0.999 is equal to 1. Wait a minute, you can't put an equal sign between things. If I hit square root button on here and I get an infinite decimal and I round it off, I don't say that's equal. I say it's an approximation. No, I'm saying this is identically equal, and I'm going to show you 3 proofs because that's where understanding what we're doing is really important. I don't do this in a lower level class. I do this in this class. So first one, if I asked you, I'm going to keep it really simple. I'll do 3 decimals. Okay, 1 minus 0.9 is 0.1. 1 minus 0.09 is 0.01. This is 0.001. This is 0.00001. Do you all agree with that? So depending where the 9 is, oh, I'm sorry. These should be, my bad. Sorry, these should be 9s. Sorry, all of these are 9s. Oops, that almost didn't fly. Okay. That 9's in the 4th decimal place, which means that 1 is in the 4th decimal place. So, well, it's going to be 0 point with some zeros. At some point, I'm going to get a 1. Agreed? At some point, I'm going to get a 1. So the question is, how many zeros do I have before I get a 1? Exactly how many? Well, exactly how many?
Infinitely many.
Yeah, aren't there infinitely many 9s? So it means there's infinitely many zeros before I get a 1, which means I never get a 1 because there's an infinite number of zeros. It's 0 point with an infinite number of zeros. There is no 1 at the other end because that would mean I'd have to stop. So because this difference is 0, that's the first proof that these are equal. Okay. The second proof, let's do what we just did. Isn't this 0.9 plus, 0.09 plus, 0.009 plus? That's what we just did. And this is most definitely a rational number because it's got a repeating decimal sequence. So this would tell me my A1 is 0.9 and my R is 0.1. So my infinite sum is what? 0.9 over 1 minus 0.1, which is 0.9 over 0.9. Okay. That's an absolute valid mathematical proof. That was 2. And now my favorite one is the oh duh. I love oh duh in mathematics because oh duh means duh. All right. 1/3 equals 0.3 with the bar. 3 times 1/3 equals 3 times 0.3 with a bar, which is 0.9 with a bar. 1 equals 0.9. kind of cool. Some of you may have seen this because when I said, what does that equal? I heard some people say 1, but understanding because of the infinite nature of the pattern, that's everything to do with this. If I stop at a finite place, no, there's nothing infinite, and then these results are not the same thing. So we've exhausted everything there is to know about a geometric series. Next one I want to look at is called a telescoping series. The name doesn't really give it a clear view. A telescoping series is basically one where your terms are going to cancel each other out in a sense. So an example of a telescoping series would be anything of the nature like this. N equal 1 to infinity of an plus 1 minus an. This would be an example of a telescoping series. You say, well, what is exactly going on here? Well, if I said, let's just write out a few terms to see what the nature is, then this would be when n is 1, I'd have a2 minus a1 plus. Now replace n with 2. Now it'd be a3 minus a2 plus. Then, and by the way, the order of the subtraction is not actually important. It's just that I'm subtracting forever and ever and ever. But what do you notice is going to happen? Cancel, cancel. I'm going to get canceling all the way down the line, but it's going to go forever. Oh my goodness. So a telescoping series is one where you can see clear behavior that things are canceling. Okay, so remember how I did the geometric series? I multiplied by the appropriate term and only the first and last terms were still remaining. That's the nature of a telescoping series. So let me give you a specific one to make it easier to digest. The simplest one we like to usually start with is the following. I want to do n equal 1 to infinity of 1 over n plus, excuse me, 1 over, the other way, 1 over n minus 1 over n plus 1. I want the bigger one first. Well, the problem is I can't write down a finite number of terms and say that's my answer. That won't work. So here's where we find the nth partial sum. Okay, we find the nth partial sum and then we take a limit of that. So let's write down the first n terms, shall we? So the nth partial sum is 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. When do I stop? Whoops, I need a dot here. 1 over n minus 1 over n plus 1. There, I've just written the first n terms. So if n was a 10, then the last term would be 1/10 minus 1/11. If n is 3, then that's the last term. This is the sum of the first n terms. You always start by finding the partial sum, because otherwise this goes forever, and what are you going to write next? So what do I know? All the adjacent terms cancel forever and ever and ever, leaving me exactly this and this. So I can say with certainty for this infinite sum, the nth partial sum is 1 minus 1 over n plus 1. For any positive integer n, this equals this for any positive integer n. So if I said, give me the 100th partial sum. Now, I asked this question recently on a discrete math quiz, and most folks just did this really fast. I gave them a finite sum, but I had like 300 terms. And then I had other people write down 300 terms and then cancel them all and didn't realize the only thing left was the first and the last. So now what is the infinite sum? Call this S, by the way. S is the limit as n goes to infinity of this, which is just 1. Beautiful. There's no shortcut, because I gave you the simplest one of all. It's not always going to be the simple. Sometimes a telescoping series is such that when you write the terms, maybe those cancel and different ones cancel. So maybe I have a couple of terms at each end left over. Until you write out the first few terms, it's hard to know which ones are canceling and which ones are left. But where you recognize a telescoping series is, first of all, you have a difference here. And you have a difference where only one of the numbers is really changing. You see, if I had an n on top and an n on bottom, wouldn't work so well. But here's a really simple example. So telescoping series, they're pretty cool. The one that we just did in my discrete class looked like this. This is what they just did. Okay. Now, at first glance, it doesn't appear that anything's going on here. But let's write out the first few terms. In other words, let's write out the first n terms. You cannot tell me what this equals. It's infinite. There's not a formula for that. So what we do is we figure out what the sum of the first n are. So if n is 1, this is 1 over 3 minus 1, so that's 1/2. If n is 1, that's 1/5. Okay, that's my first term. I am not interested in putting this over a common denominator. Plus, now n is 2, so this is 1/5, and this is 1/8. Now n is 3, it's 1/8 minus 1/11, plus it's going to go for a while, and then eventually it's going to be this. So when I'm staring at this, I go, cancel, right? This is going to cancel the next one. It's going to cancel all the way down the line, leaving me only these two terms right here. Now, this is a finite sum because it's a finite number of terms. Even if my telescoping series diverged, by the way, the nth partial sum of any series is always finite. You cannot add a finite number of finite numbers and get anything but a finite result. Now, if I had an infinite number of finite numbers, that's where divergence can come. So finally, S, my infinite sum, is the limit of this, which is simply a half. Beautiful. Very, very cool stuff. Okay. Now that's the second kind. This one's fairly simple to work with, but it's not nearly as common as the geometric. Now the next one we're going to do is one of the most common and one of the most important. The next one is something called the harmonic. The harmonic series. Now, the word harmonic is one of these ambiguous math terms because depending on the context, harmonic actually takes on several different meanings. And I don't know why, but we've given it multiple meanings in mathematics. And in a differential equations class, you're going to have maybe in the same problem, two completely different meanings of the word harmonic. So I don't like it. If anybody here has had physics, the concept of harmonic refers to motion. There's something called harmonic motion that's unrelated to a harmonic series. Harmonic motion would be if I have a hanging spring and I pull on it and it's got a weight, it's going to oscillate up and down. If I have a car with bad shock absorbers and I hit a bump, I'm going to be bouncing up and down. That up and down oscillation is called harmonic motion. Okay, that's not the same as this. The harmonic series is simply the following. N equal 1 to infinity of 1 over n. That's it. So this is 1 plus, I'm sorry, 1 over, let's start that again. 1 over 1 plus 1 over 2 plus 1 over 3, forever and ever and ever. Now the question is, does this converge or does this diverge? Now what's really interesting, I used to do this in class because it used to be, I mean, even 20 years ago, every single student in the calculus class would have a graphing calculator that they knew how to program the summations. And so I'd say, all right, if anybody knows how to do this, add up the first million terms. And so they just do on the calculator, this first million terms, and then we just sit back. And maybe an hour into class, somebody'd wave at me and go, okay, my calculator's done calculating. You got to give it some time. Calculators can't do that fast. Okay. So then they'd say, and here's the number I got. And it would be a really small number, it'd be like 14 or something. And you go, well, obviously this thing is going to converge. If I go out a million terms and I'm only 14, but the thing is, what's happening in a finite duration of time doesn't mean anything. If my first 5 terms I added up to a bazillion, that doesn't mean I'm going to diverge. You can't recognize the behavior infinitely with a finite amount of activity. So let's consider the following. If I said, let's write this down, I'm going to group this differently. I'm going to write it like this. 1 plus a half plus a third plus a fourth plus a fifth. Hold on. Oh, sorry. A third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth plus a ninth. I'm going to cheat up to a 16th plus a 17th up to a 32nd. I'll do one more of these plus a 33rd all the way up to a 64th. And I'm going to do this forever and ever and ever and ever. But I'm going to take this and I'm going to group it. And how am I going to group it? After the half, I'm going to do 2 terms, then 4 terms, then 8 terms, then 6 terms, then 32 terms, 2 to a power terms. So, well, that's a strange way of grouping it. Well, here's why. This quantity right here is bigger than this quantity right here, because 1/3 is bigger than 1/4. This quantity right here is bigger than this quantity right here, because these 3 numbers are all bigger than 1/8. This quantity here is bigger than, oops. Hopefully everybody can see that. This is bigger than this, because every one of the terms is bigger. How about over here? This quantity is bigger than this quantity. This quantity is bigger than this quantity, and I can group these forever and ever. So there will be an infinite number of groupings. Each group, right? 2 terms, 4 terms, 8 terms, 16, 32, 64, 128. Remember, I'm going forever. So the fact that some of my groupings might have thousands of terms, millions of terms in them, they go on forever. So why would we care about that? That means my sum right here that I have is bigger than 1 plus a half. By the way, a fourth plus a fourth, that's a half. How about an eighth, an eighth, an eighth, an eighth? 4/8. Oh, that's a half. And here I have 8 1/16. That's a half. Oh, and that's a half. And that's a half. I said I can group these forever. And as long as I group them in this pattern, my harmonic series adds up to a number that is larger than 1 plus a half forever. If I add up a half forever, what will that be? Anybody? I'm going to add up infinity. As crazy as it is, this is infinite. And the coolest part is, no matter what technology you're using, if you have it add up to a finite amount, I don't give you add up to a billion, it won't add up to a very big number. But the fact is you're adding forever. So it takes a while, but it grows without bound. This is the proof. I love this proof because it's like, oh my gosh, who thought of this? You see, as long as I group them in such a way that each grouping is always going to be bigger than a half, and there's an infinite number of groupings. So I group into something that's bigger than an infinite number of halves. Yeah, but I'm only half of infinity. Isn't that cool? So the harmonic series diverges. Now, there's a whole bunch of little things we can do with that. So right off the bat, the harmonic series diverges to infinity. And that's a huge result that we're going to use all the way through the course. So what if I did the following? Just as a general statement, I think I did something like this before. I want n equal 1 to infinity of an. Question, is that the same as saying n equal 1 to k of an plus n equal k plus 1 to infinity of an? Stare at that for a moment. Are these equal? K is some finite number. Are these equal? This is the sum of the first k terms. This is all the rest of them. Is it equal to this? Just yell out what you think.
Yes.
Yes. And here's the critical thing. No matter what's happened with this guy, no matter what this guy's doing, absolutely, this is finite. No matter how ugly it is, this is finite. I just added a finite number of finite numbers. Now, it's what's happening the rest of the way that determines. So either both of these quantities right here converge, not to the same number. No, they'd converge to this plus this. These either both converge or these both diverge. See, if the remaining terms diverge, then the whole thing diverges. If the remaining terms converge, then the whole thing converges. So it never matters. This is the craziest part. It never matters where you start if you're asking the question converge or diverge. It never matters. I don't care if you start at the 10 millionth term, because if you're lopping off the first 10 million terms, that's still a finite number. But the rest of the way, if it's infinite, then it's still infinite. It never matters where you start if it converges or diverges. Where you start will only affect what it converges to. Suppose this converges, and now I've removed a whole bunch of terms. Well, this is going to converge to just a smaller number because I removed that stuff. That's all. It's still going to converge. It just won't converge to as big a number. So with that statement there, I'd like to know n equals 100 to infinity of 1 over n. Huh. What do you think? Converge or diverge? This is
Diverge.
This is 1 over 100 plus 1 over 101, forever and ever and ever. Well, isn't this equal to oops, yeah, make sure I got that right. I'm starting at 100. That means I ignored the first 99 terms. Hopefully you recognize that. So wouldn't that be the same as the entire thing minus the first 99 terms? Yeah. And we know that's finite. And we know that's infinite. So if I take infinite and I subtract a finite amount, I'm still infinite. This is still infinite. So just because I removed a few terms, it doesn't affect whether it converges or diverges. That's what I was saying. So we have a really funny way of describing this mathematically. This guy here, it starts at 100. This is a harmonic series. I always had fun with this when I was in school. This guy here, the harmonic series. When someone says the harmonic series, they mean this one. But if they say a harmonic series, they're saying we might be starting in another place. We might be starting at 7, 31, 2. A harmonic series is anything where I have the harmonic series, but maybe I start a little later. But we call that one the. There are infinitely many harmonic series, but there's only one the harmonic series. Right? This is kingpin, I guess, right? Big fish, whatever you want to call it. So harmonic series diverges. Main thing we got to get across. So if I manipulate a harmonic series within a problem, that's really important. Now, here's where we can get into trouble. This is why big picture is sometimes better than isolated details. We just did a telescoping series a moment ago. We did this problem right here a moment ago. Okay? And we just concluded that the value of this series was 1. And we did it by taking a limit and all that stuff. But is the following statement true? Is that a true statement mathematically, what I have right there? What do you think? True or false?
True.
False.
True. We know the summation of a sum is the sum of the summations. Yeah, I can pull it apart. That's absolutely the same thing. Problem is, oh, so is pulling it apart a very good idea in this case? No, because that's infinite. That's the harmonic series. That's a harmonic series. See, this one started at 1 over 1. This one started at 1 over 2. I just removed the first term. Okay. Everybody see that? That's not useful pulling them apart. Because now I'm like, I don't know what to do with it. No, it was actually easier to work in this capacity. Now we're going to go over the last rule of the day, and this one's really, really huge. Okay. Now I'm going to introduce a logic concept to you that you may never have heard before. There's something called necessary and sufficient conditions. Mathematically speaking, these are very, very powerful logic statements. Necessary and sufficient conditions have to do with outcomes. My favorite example to use is a necessary condition for us to win the game today, our team to win the game today, is for us to actually show up. That's necessary if we want to win the game, because if we don't show up, we lose. Now, does showing up guarantee we're going to win the game? No, we might get destroyed, but at least there will be a game and we have a fighting chance. A necessary condition for us to win is that we show up, because if we don't show up, we don't win. So anytime you have a necessary condition, it means that if that condition does not happen, then the conclusion cannot happen. A sufficient condition for us to win today is that we outscore the other team. So if we outscore the other team, we win, because that was enough to win. A sufficient condition, if it happens, the conclusion is guaranteed. Oh, so I have if A, then B. A necessary condition is if A doesn't happen, B is not going to happen. A sufficient condition is if A happens, B is guaranteed to happen. It sounds a little confusing. Necessary is weak, sufficient is strong. So there's a necessary condition for convergence of any series. That doesn't mean if you fulfill this requirement, you're going to converge. It means if you fail to fulfill this requirement, you're guaranteed to diverge, because it's only a necessary condition. So now I want you to understand the difference of those terms. Some folks get confused by that. So we say a necessary condition, oops, for convergence is there are two things that have to occur. Okay. First, the limit as n goes to infinity of an is 0. So in terms of a sequence, it means my sequence converges to 0. And second, that absolute value of an plus 1 is less than or equal to the absolute value of an for all n greater than n. Now I'll explain that one in a moment. That looks really weird and vague and ambiguous, but it's actually really simple. So the first condition says my terms actually have to be approaching 0. You see, what if my terms were approaching, what if the limit of my ans, they're all approaching the number 3? Then it's kind of like saying I'm adding up the number 3 infinitely many times. So if I'm not approaching 0, that means I'm adding up positive finite numbers forever, never, never. Clearly, I would diverge. This one says my terms are getting smaller in size. The sign doesn't matter. It just matters that they're getting smaller in size, even if those signs are changing. So the absolute value, because there's nothing wrong with a negative number in your series. This says forevermore. That says for all n greater than some arbitrary amount. So in simple English, that means at some point, maybe it's the very first term, maybe it's 25 terms down the road, maybe it's 1,000 terms down the road, at some point when my subscript is bigger than some fixed number, let's just say it's the 100th term, from that point on, all of my terms are getting smaller. So that means early on, my terms can be bouncing up all over the place. They can be getting bigger, they can go crazy, but at some point, they're going to get smaller forevermore. That's what the second condition says. If my terms never get smaller, if they're only getting bigger, then I'm not going to converge. If I fail either one of these, I diverge. So because I'm looking at the an, this has two names. My favorite is universally, this is usually called the Nth Term Test. I'm taking the nth term and I'm saying does it equal 0 and is it getting smaller? Okay, the Nth Term Test, that's my favorite. Some textbooks vaguely call this a test for divergence. And I don't like that name because it's too vague. We have every test we're going to learn over the next couple of weeks are different versions of tests to determine convergence or divergence. So I don't like this one because there's too many other things that could easily fit that bill. So I like using the Nth Term Test. And what the nth term test means, it's a necessary condition for convergence. But passing the nth term test does not mean you're going to converge. Failing the nth term test guarantees divergence. And I'll show you this. Okay. One of these we're going to look at next day. We're not going to look at it today. Right now, I'm going to tell you the following. N equal 1 to infinity of 1 over n squared. This one converges. We're going to prove this next day. I'm just going to tell you that right now. But we also know, we know this one diverges. We just proved it. This is the harmonic series. And I want you to notice, both of these series, both of them, if I take the limit as n goes to infinity of 1 over n squared, that's 0. And 1 over n plus 1 squared is always smaller than 1 over n squared. We'd say for all n greater than or equal to 1. For every single number in this series, the terms are getting smaller. So this guy right here passes both pieces of the nth term test. Well, what about this guy? In other words, my big capital N. The harmonic series, the terms are approaching 0 and the terms are getting smaller. So the harmonic series passed the nth term test. Oh, okay. So passing the nth term test doesn't mean you converge. It means it's worth considering. So the way it's going to work, we're going to learn how to attack every possible form of a series you'll ever see. And when you look at it, you're going, hey, wait a minute, I think it's going to fail the nth term test. If I can show it fails the nth term test, I'm off the hook. I'm already done with the problem. Problem's a piece of cake. But if I take time and trouble and it passes the nth term test, it hasn't told me anything. I still got to run all my regular diagnostics, if you will. So you only apply the nth term test if you think it's going to fail. That's it. You never apply it when you think it's going to pass, because passing the nth term test doesn't guarantee convergence. See, this diverged, yet it passed. So you apply it when you think it's going to fail. So let's do an example of that. So I want, let's say, here's my series. I'd like to know if this converges or diverges. Well, I don't even know how to attack that, except, wait a minute, I do know one thing. If I take the limit as n goes to infinity of 3 minus 1 over n squared, what will I get? What is that?
3.
3. And more importantly, it's not 0. So in simple English, it's kind of like saying I'm going to add up the number 3 forever. We're done. This diverges. Why? Because I fail the nth term test. That's how the nth term test works. Nth term test. I just showed that the limit was not 0. I'm done. There's nothing else to do. Great. This diverges. Now, what kind of divergence? Well, since every term's positive, it's probably going to diverge to infinity. But more importantly, it diverges. Now, right now, we don't know any tests to prove convergence, not yet, except if it's geometric or telescoping, we know how to show if it converges or not. If I gave you a geometric series, you don't run an nth term test, it's geometric. You just use the properties of a geometric series. If I give you a telescoping series, you do the same thing. You use the properties of a telescoping series, because of all of the series that we will ever deal with, the determination of convergence or divergence is your ultimate goal. But only in a geometric or a telescoping series can we actually determine what it converges to. Now, this is kind of strange. I said a moment ago, the sum of 1 over n squared converges. But in general, trying to calculate what it converges to, we don't have a way of doing that. That would actually require basically a computer technology. So our goal is simple. We determine if a series converges. If I now needed a numerical value, I would then use a computer to do a calculation. But the computer can't add infinitely many. No, that's true. But for a series to converge, we're going to show we haven't already started showing it, for something to converge, the terms not only have to approach zero, they actually have to approach zero very, very quickly. They have to be getting small and they have to be getting small fast. You see the harmonic series, the terms got smaller and they approached zero. They just didn't get small fast enough. Ah, okay. So if the terms are getting really small, really fast, then if I use technology, I go out a fairly large number of places, I'll realize, oh my God, my terms are microscopic. I got lots of zeros after the decimal place and they're getting smaller. I can actually give you reasonable approximations to as many decimals as you need accurately if I know it converges. So our goal is to prove convergence, use technology to find the answer if necessary. Because if it diverges, it doesn't matter about technology. There's no number you can calculate. So if nothing else from today, be able to identify and evaluate any geometric series, any telescoping series, and be able to identify a harmonic series. Because if you can do those, you're in good shape. So the next quiz you're going to be doing is going to have all those kinds of things. So let me go ahead and stop here.